Okay, so we're recording. And this video will be on the Unit 2C handout that we worked on in class. Now in class, I don't think we made it to the second page here. I'll probably fill it in anyway, but just so you have it. Okay, so this thing right here, that thing is the way that we typically are going to prove stuff in class. We're going to use something where statements go on the left side, and then for every statement you make, you have to give a reason why you're allowed to say it. So, and since this is the first proof that we're going to do formally, it'll take a little while to get used to kind of how this works. So, in the picture over here, in the directions it describes this, it says angle 1 and angle 3 are called vertical angles. And it turns out that angle 2 and angle 4 are also a pair of vertical angles there. Vertical angles are just basically, if you can make an X out of them, they're ones that are opposite each other like that. And it turns out, and a lot of you already seem to have known this based on looking at your homework and stuff, is that vertical angles are congruent. They're exactly the same shape and same size. So what we're going to do is we're going to pretend that we don't know that's true yet, and we're going to prove it. So we're going to show that angle 1 and angle 3 we know that they're vertical angles, and we're going to prove that they're congruent, which is really the same thing as saying prove that they have, sorry, I'm outside, so you might hear that crow, prove that they have the same number of degrees in them. The measurements are equal. Okay? So the way that we do this is we're going to start out by saying the given info. Right? That's how you normally start a problem, is you list off what you know. So angle 1 and angle 3 are vertical angles. And the reason that we know that is it's given. Right? That's given info. So that's a common way to start a proof. Now the last step, in this case we're going to take 6 steps. The last step is going to be that angle 1, measurement of angle 1, is the same size as measurement of angle 3. It's equal to measurement of angle 3. And we don't know the reason that that's true yet. That's the same thing as saying angle 1 is congruent to angle 3. I'll put that behind it here. Oh man, that crow's like right above me. So right here I'm going to say, or angle 1 is congruent to angle 3. Those are interchangeable. Remember, congruent is for the actual objects being the same, and the measurements meaning the degrees are the same. Okay, so somehow I want to get the 1 and 3 involved. Well, let's come up with an equation that involves the 1. So one of the things we can do is we can say 1 and 2 put together add up to 180 degrees. Right? So measurement of 1 plus measurement of 2 equals 180. And the reason that that's true is, well, they're 2 angles next to each other added up to make the big angle. That's the angle addition postulate. Okay. Well, we also need, so now we've got m angle 1 involved. We also need to involve somehow m angle 3, measurement of 3. Well, if you look at 3, we could do something similar, like 3 plus 4 equals 180, or 3 plus 2 equals 180. Well, I'm going to include the 2 since we already used it right here. Right? So if we kind of use it again, maybe that would be more useful. So I'm going to say measurement of 3 plus measurement of 2 equals 180. And that's because 2 angles next to each other add up to form the big angle, which in this case is 180 degrees. So that's also the angle addition postulate. By the way, if you like doing this, so let me move this over. If you use the same reason twice in a row, you can do that quotation thing, and that means just whatever's right above it, and I'll count that if you want to do that. But since I already wrote it, I'll just put it right here. Okay. So now, here's a common trick that gets used. Notice there are no 180s involved in the final thing that we're trying to prove. So right here, notice this equals 180. And this equals 180. And since they both equal 180, I'm allowed to take this green box and put it right there in place of the 180 because it is 180. So if I do that, then I'm going to write measurement of angle 1 plus measurement of angle 2 equals the measurement of angle 3 plus the measurement of angle 2, right? And so I'll kind of highlight these boxes. Here's the blue box, and we knew that was 180. And here's the green box, and we knew that was also 180, so they're equal to each other. And when you replace that 180 with the other term that equals 180, that's substitution. Okay, so now we got that. Well, if you look at line 4, and I ask you to simplify it somehow, you might notice m angle 2's on the left and m angle 2's on the right. And so we could get rid of them by subtracting them out. And before you subtract it out, you do this little step here. It's kind of like this. If I said 4x plus 3y equals 4x plus 10. What you would normally do is just subtract out the 4x's. And what a lot of students do is they write the 4x under here and the 4x under here, and then you subtract. So if I subtract, the reason you do that is because you're saying the amount I'm going to subtract on this side is the same as the amount I'm going to subtract on that side. So even though it seems kind of dumb, you say equals, and then you actually subtract them. So the 4x's go away and I get 3y here equals 4x's go away and I get 10 over here, and then you can keep solving. So over here I'm going to say the 2 that I'm going to subtract from this side, from this side is the same as the 2 I'm going to subtract from this side. Right, I'm just kind of lining them up there. Whenever you say something equals itself, that's called reflexive. It's kind of like reflective. That's how a lot of students tend to remember that one. And then what you can do is you can just subtract straight down, and you've got 1 plus 2 minus 2 is just 1, and 3 plus 2 minus 2 is 3. And so the way that we get to the last step here is subtraction. Okay? Now, I'm going to bounce back and forth. I'm going to do this video the same way that I did the lesson in class. So at this point, this was our first proof, and then we came over to the other handout, Unit 2 Reasons. Okay? So over here in this proof, we have some reasons, and these are things that we've talked about at various points in class. Well, in Unit 2, we're going to have a ton of possible reasons that can show up here. And so this is the list of every reason that you could possibly come across. Like, for example, there's reflexive, there's substitution, right? So let's go through them, and I'll kind of fill in these mini proofs that are on the right for some of them. Now, given, there's no, you know, if something's given, you don't really need a mini proof to show why it's given. It's given. So let's talk about definition of midpoint, because we've actually done this before, we just haven't formally talked about it. So the definition of midpoint, the way that you use that as a reason in a proof is you have to know something first. You have to know something like M is the midpoint of AB, right? For whatever reason, maybe you proved it using substitution or something like that, maybe it was given. I don't know what the reason is for that. But somewhere in the proof, you have this step. Well, if you know that, then the very next line could be that since m's in the middle, this part equals this part. So you could say AM is the same as MB. You can either say the lengths are the same, or if you wanted to, you could say the segments are congruent to each other. And technically you're supposed to put the bars over the top, but I'm not going to be picky about it because it seems like the further up you go in math, the less people care about that bar. So if you're saying because m's in the middle, you know that this side equals that side, the reason that's true is because, well, m's the midpoint. That's what a midpoint's definition is. Definition of midpoint. Now it also works in reverse. If you have this diagram and you forget about what I just wrote up here. Pretend we didn't do that. If you already somehow know that this equals this, somehow you already know that AM and MB are the same, right? Or that they're congruent. For whatever reason, who knows why we know that? Maybe you use substitution somehow, right? Maybe it was given. Well, if that's the case, you can then say, based on the picture, because M is on that segment AB, M is the midpoint of AB. And that's also because, well, that's what a midpoint is. It's the definition of a midpoint. Okay, so we're going to do the rest of this first page here, and then we'll bounce back to the other handout. So let's talk about angle bisector. Now, angle bisector is kind of the angle version of the midpoint in number 2. So one thing that we could do is start out with, well, let's say that we knew BD was a bisector. So BD bisects angle ABC. And that's, oh, it's either given or somehow we figured it out. ... Whatever reason, right? Well, if we know that, then that means that this part of the angle equals that part of the angle. So I can say one of two things. Either you can say angle ABD is congruent to angle DBC. The two little guys are exactly the same shape and size. Or you can say the measurements of them, the degrees are the same. And these kind of mean the same thing. You're allowed to do either one and interchange them. That's okay with me. And the reason for that is, well, because we had a bisector right there. So it's definition of angle bisector. Notice I abbreviate a ton because it's sort of a pain to keep writing out everything word for word. Now, just like midpoint, the definition can go in reverse too. So if for some reason you knew that the two little angles were already congruent, or you knew that they had the same number of degrees, for whatever reason, somehow you solve for that, or it was given, then you can say, well, since this angle and this angle are the same, BD has to cut them in half. So BD bisects angle ABC. And the reason for that is, well, that's what an angle bisector does. If the two little guys are exactly the same, then BD has to bisect them. Definition of angle bisector. Okay, so you can kind of see that these two are related. The midpoint and the bisector each say one small part equals the other small part. Okay. We've got these two theorems down here, midpoint theorem and angle bisector theorem. Oh, I don't know why 6 is there. Excuse me. Okay, so don't worry about this part right here. Okay, so the midpoint theorem is kind of like the midpoint definition, but there's only one version of it. In this one, we start out with the same thing. You have to know somehow that M is the midpoint of AB. For whatever reason. Usually that's a given one. Okay, well, if M's the midpoint, if it was the definition of midpoint, we'd say this part equals that part. But that's not what the theorem says. The theorem relates this part to the whole thing. So if you think about how those are related, AM is half of AB. Notice it's a little different. It doesn't say one small part equals the other small part. It says one small part is half of the whole. And the reason is called the midpoint theorem. Okay. And then down here, the angle bisector theorem is just like the midpoint theorem, but in like the angle world. So in this one, we've got, you need to know somehow that BD bisects angle ABC for whatever reason, right? Probably given, but maybe you proved it somehow earlier in the proof. Well, if that's the case, well, we know from the definition that this little angle equals that little angle. But just like the theorem up here, they relate the small angle to the whole angle. So the way that those are related, you can say that measurement of angle ABD is half of the whole angle ABC, right? And the reason for that, angle bisector theorem. So notice the midpoint and angle bisector theorem, they're not the same as the definitions, which say one small part equals the other small part. Instead, they say one small part equals half of the whole thing. Right? Okay, so let's go back to 2C now. So in 2C, let me get rid of this because we don't actually need that. In 2C, there's a question here. What's the difference between definition of a midpoint and midpoint theorem? Definition of a midpoint says one small part equals the other small part. Whereas the theorem says one small part equals half of the whole thing. Right? They're related for sure, but they don't quite say the same exact thing. Okay, so we'll do number 3, and then I'll stop the video there because that's what we did in class so far. So number 3 says, prove the midpoint theorem using this partially filled in structure here. Now, the midpoint theorem is what this says right here, but when you're trying to prove something, you're not allowed to use it in its own proof. You can't use it as a reason. So, because otherwise you could just say, here's the given, and then the next step would say there because of the midpoint theorem. But you're not allowed, if you're trying to prove the midpoint theorem, you can't say the midpoint theorem works because it's the midpoint theorem. That's not good reasoning. So let's draw a picture for it. M's the midpoint of segment AB. So here's AB, and here's M. So we're going to prove that AM is half of AB. So a good starting point almost every single time will be list the given. M is the midpoint of AB. Given. Okay, so we know M's the midpoint. Well, based off on that, we can then say AM and MB have to be the same length. AM equals MB, or you could say that the two segments are congruent to each other. Either one is fine with me. I'm going to usually go with that one, I think. So AM and MB are the same. Well, it's not because of the midpoint theorem, it's because that's what midpoints do. If we come back to our reasons over here, M is the midpoint, so one small part equals the other small part. That's what we just said right here. M's the midpoint, so one small part equals the other small part. That's definition of midpoint. Okay, so let's look at the next step. AM plus MB equals AB. AM plus MB equals the whole thing. Well, that's not actually related to the midpoint there. That's because A, M, and B are all on the same line, all on the same segment. That's the segment addition postulate. That's part of the reason I was drilling that in last unit. Right? You're allowed to add up the two segments next to each other to get the whole. All right, now notice this next one says substitution. And the last step, so let's skip 4 for a second. The last step is always what you're trying to prove. AM equals half of AB. So notice that this last step here has an AM in it, and it has an AB in it. This step has an AM in it and an AB in it, but somehow it also has an MB in it, which we don't really want because there's no MB in the final equation. So the goal is to somehow get rid of the MB. Well, that's why step 2 comes in handy. Step 2 says MB is the same thing as AM. So anywhere that an MB appears, I can replace it with an AM. So right here, I'm going to replace that MB with AM. Right? So this turns into AM, AM here, plus, and then this MB I'm going to replace, because of step 2, with another AM equals AB. That's the substitution. I'm substituting replace MB with AM, since step 2 says that's okay. Says we can do that. Okay, now another way of thinking of that, 2AM, whoops, equals AB. So now if you look at this line, 2AM equals AB. Well, in order to get from 2AM equals AB to the next line, you either divide both sides by 2 or you multiply both sides by a half. So that's multiplication or division. However you want to think about it is fine with me, because really it's the same sort of idea. And that's the proof of number 3. So now that we've proven it, the idea is you can use it in other proofs if you wanted to. So that's the end of that. Hopefully that's made some sense to you. It'll take a little while before this stuff feels intuitive. It's really one of those things that you just kind of have to practice enough proofs, and then you start to see how they work, and you kind of can predict what sort of patterns are coming. So I hope that helps a little bit, and I'll see you in class soon.